Hi all, welcome back to KIG1002 Dynamics. In our last lectures, we discussed about the kinematics of particles, particularly on rectilinear motions. So today, in our lectures, we will look into kinematics of particles, curvilinear motions. This is the outline of our today's lectures. Like our last lectures under rectilinear motions, today we also look into the kinematics of particles in terms of its positions, velocities, and accelerations under curvilinear motions. These curvilinear motions will be decomposed into rectangular components in terms of velocity and accelerations, and we will also discuss how we make use of these informations to solve dynamics problems that involve curvilinear motions. In our last lectures, we introduced the concept of relative motions. So in today's lectures, we will try to make use of these relative motions concepts to frame that in translations. Beside the rectangular component decompositions, we also can decompose the motions into tangentials and normal components, as well as radial and transverse components. So in today's lectures, we will be looking into how this decomposition works and how we can use it to solve dynamic problems that involve curvilinear motions. Curvilinear motions of a particles is defined as the particles moving along a curve other than a straight line. So this is the examples of curvilinear motions. The softballs and the car both undergoing curvilinear motions. So here we will want to determine the geometry of the motions or the kinematics of the motions in terms of its position, velocity, accelerations when the bat hit the softballs, or how the car is moving along this curved pathway in terms of its positions, velocities, and accelerations. Let's have a look on these figures. To define the position P occupied by the particles at a given time t, we can first select a fixed reference system with the axes of x, y, and z. We can then draw the vectors r joining the origins O and P. The vector r is characterized by its magnitude r and its direction with respect to the reference axis. So this is the directions. So this basically completely defines the position of a particle with respect to those axes. The vector r is referred to the positions vectors of the particles at time t. So position vector is defined as for any particles at time t, the vector between the origins O of a fixed reference frames and the position occupied by that particles. So if now we consider the vector r primes, defining the position p prime occupied by the same particle at a later times t plus delta t. So this vector delta r joining p and p prime represent the change in the position vector during the time interval delta t. So what it means here is the particles moving from position p to p primes at the time interval of delta t, and the change of position is delta r's. The vector r primes is obtained by adding the vectors r and delta r according to the triangle rules. The average velocities of the particles over the time intervals delta t is defined as the delta r over delta t. So the average velocity of these particles is defined as the r dt. The delta r is a vector and the delta t is a scalar. So these average velocities, delta r, delta t is vectors in the same directions of delta r's and equals the magnitudes of delta r divided by delta t. So here, this delta r, delta t is what we have called just now the average velocities. The instantaneous velocity of the particles at time t is obtained by choosing shorter and shorter time intervals of delta t. Correspondingly, shorter and shorter vector increments of delta r. So we can write in an equations the instantaneous velocity, which is the vectors v, equals to when the limits of delta t is approaching 0 for the average velocities delta r over delta t. We can rewrite it as equals to dr dt. So when the delta t and delta r become shortest, so the p primes basically move to near to p. That gives us our instantaneous velocity equals to dr dt. And at this case, the vectors v of the particles at time t is actually at the tangents of the path of the particles. Tangents of the path of the particles v. The magnitude of these vectors v, or it can be seen from here, this vector v, which is the tangent of the path of the particles, can be obtained by substituting this delta r into the formulas. Right? We can also say that when the delta t decrease from p prime to p, from p prime to p here, this is very similar or very close to the length of delta s from p to p naught. So if one wants to determine the speeds of the particles at positions p, we can determine these speeds, or what we call here instantaneous speeds, which is a scalar, as when the limits of delta t is approaching zeros, ds or delta s over delta t. So in this case, it can be determined or equals to ds over dt. If we consider the velocities vectors v of the particles at time t, which is this one, and its velocities v primes at the later times t plus delta t. So if we can draw these two vectors v and v prime from the same origins o primes, we have these x primes, y prime, z prime in a different coordinates systems. Then we will have our v, we have another one's vectors at a later stage v primes. So I will call this as q. So if you trace this out, so at q and q prime. So the vectors that joining q and q primes is here, we call it delta v. It represents the change in the velocities of the particles during the times intervals delta t. So the vectors v primes, which is this one, v prime, can be obtained from v prime can be obtained by adding the vectors v plus delta v. So v primes equals to v plus delta v. So this delta v is a change in the directions of velocities, as you can see, as well as change in speeds. So to obtain the average accelerations of the particles over the time intervals delta t, so the average accelerations is then defined by our delta v over delta t. Similarly, like what we have observed in velocity just now, the instantaneous accelerations of the particles at time t is obtained by choosing smaller and smaller values of delta t and delta v. So it can be represented by the vectors a, as you can see here. So it's equals to when the limits of delta t is approaching 0 for the average accelerations delta v over delta t. It can also be rewritten or simplified as dv dt, which we are more familiar with. We can observe that these accelerations is the tangents to the curve that what we have described by the tips of q vectors. Let me show you. So we are saying that the accelerations a is at the tangents of this curve from q to q primes. But please remember that this coordinate system is at o primes. It's not o, right? So in general, we want to say that the accelerations vectors is not tangents to the particle's path. So in the original coordinates with the origins at O itself is referred, the accelerations is not in the tangents to the particle path, or the velocity vectors. The curve that we have described by the tips of V, as you can see here itself, this curve where you give you the acceleration, which is the tangents of this particular curve itself, we call it as a hodograph of the motions. Remember that it is under different coordinates. In general, in the original coordinates with the origin at O itself, you can see that this is our position vectors R, and we know that the path of the particle itself, okay, basically it will give us the velocity of the particles is under the tangents of the path of the particles, but the acceleration is not under the tangents of the particle path or the velocity vectors. So it is under these O primes origins itself. Yes, it is the tangents of this V to V prime curve. We learned that positions is a vectors, position vectors, velocities and accelerations, they are also the vectors. So when the positions of a particles P is defined at any instance by its rectangular coordinates x, y, z, for example here, R, the position vectors equals to x in terms of I plus yj plus zk. So it's very convenient to resolve these velocities vectors and acceleration vectors of the particle into rectangular components. So if we are differentiating the position vectors by ones, then we will have our velocity vectors v equals to the dr dt, if you still remember, r dt. Then if we decompose it in terms of the rectangular components, then we have dx dt, I, dy dt, j, and dz dt k, right? So the first derivative of this x, y, z with respect to t is what we having here, x naught, y naught, and z naughts. So this x naught is the first derivative of the positions in terms of x with respect to t. Then we are actually having the velocities in terms of x directions. Similarly, with y naught, we have velocity in y directions, and z naught is velocity in z directions. If we differentiate another times from the velocity vectors, we will have our acceleration vectors, right? Noting that our acceleration vectors is dv dt, so or equals to double differentiations of our position vectors. So here it will become d2x dt square I, d2y dt square j, and d2z dt square k. So in other words, it is x double dot I here, x double dot I plus y double dot j plus z double dot k. So here we can say that our x double dots double differentiations of positions vector in x directions will be our accelerations in x directions. Y double dot equals to ay, and we have z double dot equals to az, the acceleration in z directions. The use of these rectangular components to describe the positions, the velocity, and the accelerations of particles is particularly effective when the components ax of the accelerations depend only upon the time t, x, the positions, and or the velocity in terms of x directions. And when similarly our ay, the acceleration in y directions, depend only upon the times, the position at y directions, and or the velocity in y directions. The same go to az upon the time, the position in z directions, and or the velocity in z directions. In other words, the motions of a particle in the x directions, its motions in the y directions, and its motions in the z directions can be considered separately. In the case of the motions of a projectiles, the rectangular components particularly effective when components acceleration can be integrated independently. If the resistance of the air is neglected, so here the motion of a projectile, we have our ax equals to x double dots, acceleration x directions equal to 0, ay equals to y double dots, we have our acceleration in the y directions equals to the gravitational accelerations, negative g, and az equals to z double dot, here is equal to 0. Denoting that x naught, y naught, and z naughts are the coordinates of guns, and by Vx naught, Vy naught, and Vz naughts are the initial velocities of these projectiles or bullets. If we integrate twice, we have our Vx. Let me write in here. Our Vx will be equals to x naught will be equals to Vx naught. Similarly, our Vy will be y naught equals to Vy naught minus gt, and our Vz equals to z naught equals to Vz naught itself. Right, if we integrate another time step, we will have our positions equations. We will have our x equals to x naught plus Vx naught t. Our y position will be y naught plus Vy naught t minus 1 over 2 gt square, and our z position will be z naught plus Vz naught t. So if we assume that the projectile is fired in the xy plane from the origin O, so we will have our x naught here. We will have our the initial conditions x naught equals to y naught equal to z naught equal to 0 when we assume is fired from the xy plane from the original O. At the same times, xy planes, we do not have our initial velocity in z directions. The Vz naught will be equals to 0. So these 6 equations will basically becomes Vx equals to Vx naught, Vy equals to Vy naught minus Gt, Vz equal to 0. while the positions equations, x equal to vx not t, y equals to vy not y minus 1 over 2 gt squared, z equal to 0. So from these equations, we can see that the projectile remain in the xy planes. Its motion in the horizontal direction is uniform. Horizontal directions, you can see that is uniform, and you have a constant velocities. Its motion in the vertical directions is uniformly accelerated. You can see that it is uniformly accelerated where you have a constant accelerations. So here, the horizontal direction is having uniform motions with constant velocities. Whereas the vertical directions is having the uniformly accelerated motions with the constant accelerations. So in summary, we can say that the motion of our projectiles could be replaced by two independent rectilinear motions. In the preceding sessions, we said that a single frame of reference can be used to describe the motion of particles. In most cases, these frames was attached to the Earth and was considered as fixed. Situation in which it is convenient to use several frames of reference simultaneously will now be analyzed. If one of the frames is attached to the Earth, it will be called a fixed frame of reference, and the other frames will be referred to as moving frames of reference. However, the selection of fixed frames of reference is purely arbitrary. Any frame can be designed as fixed. All other frames not rigidly attached to this frame will then be described as moving. In other words, we can make use of what we have learned in the previous chapters, the relative motions of particles, to determine the motions of several frames in translations, either in space, 3D, or in 2D, XY planes. Some of the examples in these topics are as shown here. So a soccer player must consider the relative motions of the ball and her teammates when making a pass. Another examples for pilots of an aircraft, the pilots have to make sure or determine the relative motion of his aircraft with respect to the aircraft carriers to make a safe landings. Let's consider two particles A and B moving in space. The vectors RA and RB define their position at any given instance with respect to the fixed frame of reference O, X, Y, Z. And now, if we consider a system of axes, X prime, Y prime, and Z primes, centered at A and parallel to the X, Y, and Z axis. While the origin of these axes move, their orientations remain the same. The frame of the reference A, X prime, Y prime, Z primes is in translations with respect to O, X, Y, Z. So here the vectors R, B, A joining A and B define the positions of B relative to the moving frames A, X prime, Y prime, Z primes. So in short, we can say that RBA is the position of B relative to A. So here RB equals to RA plus RBA. RB equals to RA plus RBA. That is what we have learned in our preceding sessions. If we differentiate once, we will have our velocities or relative velocities equations. Here, VB equals to VA plus VBOA, and our VBOA is the velocity of B relative to A. And if we differentiate again, we have our accelerations informations. Accelerations AB equals to AA plus ABOA. Our ABOA is the accelerations of B relative to A. The absolute motions of B, the particles B, from here we can be obtained by combining the motion of A with relative motions of B with respect to moving frame attached to A. So if we have the informations of VA or AA together with the relative motions of VB over A or AB over A, then we can determine the absolute motions of VB or AB. In previous sessions, we note that the velocity of a particle is a vector tangent to the path of the particles. But in general, the acceleration is not tangent to the path. We can make use of these informations to analyze the kinematics of a particle under curvilinear motions. For example, the motion of the racing car on the racetrack, the trains on the curved track, the roller coaster on its track. If we have an idea of the path of these vehicles, for example, the radius of the curve, it's very convenient to analyze these motions using tangentials and normal components. Sometimes it's called path coordinates. So let's have a look on how to determine the curvilinear motions of particles in terms of tangentials and normal components. First, let's consider a particle which moves along the curve contained in the plane of the figures, the xy planes. The tangential directions ET is the tangent to the path of the particles. We note that the velocity vectors of the particles is in these directions. The normal directions EN is the perpendicular directions to ET and points towards the inside of the curve. The accelerations has components in both EN and ET directions. Assuming the R is the instantaneous radius of the curvatures, this is the R. At this particular point, this is the R. Then we have our velocity vectors is V in the ET directions, in these directions. So it's a vector tangent to the path of the particles. If you still remember what we have learned earlier, the accelerations is not tangent to the path. Probably it will go into these directions, A. Right. So this vector A or acceleration is, if we decompose in the directions of ET and EN, the tangential and normal directions, then it basically will give us two components of accelerations. A equals to dv dt in the directions of ET plus v squared over rho or r, the radius, in the directions of En. So in the case of we have particles at this particular point now, we want to determine its velocities and also accelerations. So at this particular point, we know that the velocities vector is tangents to the path of the particles, then we will have this is our v equals to vt et in these directions. Then we have these directions is our en directions, right? So to get or to determine our a or accelerations, we will have the components of the tangential parts et. In this particular part, we have this at, and in this particular component, we have this an. Basically, give us the accelerations vectors. So let's have a look on how to derive these acceleration vectors in tangentials and normal components. First, we have to define the motions of our particles as shown in the figures here. So P is the position of particle at a given instance. So we will have the components in the tangential et and also en in normal directions. When the particles move from position P to P primes at a later instance, we have these et primes to be the unit vector corresponding to that position at P primes. If we draw both vectors, et and et primes, from the same origin O primes as you see here, so this delta t is actually equals to et prime minus et. So since this et and et primes are of unit lengths, their tips, right, lie on a circles of radius 1. So if we denote delta theta here, delta theta is the angle formed by et and et primes, then we can find the magnitude of delta et. So how to find this delta et? So if we can cut it to half, then this is 90 degree. Then we have this delta theta over 2. Then we have this equals to delta et over 2. Getting the sign, delta theta over 2 is actually equals to delta et over 2 divided by this unit length 1. So giving us our delta et equals to 2 sine delta theta over 2. So when we take the limits of delta theta is approaching 0 for delta et over delta theta, meaning when this delta theta is approaching 0, the vectors will become the tangents to the unit circles. So the vectors now is, these vectors now is becoming the tangents to the unit circles of these figures. And you can see that it is perpendicular to ET. So here we call this as our EN, our normal components, EN, vector in EN directions. So this EN is similar to what we have seen here, EN, which is perpendicular to our ET when the delta theta is approaching 0. So in other words, if this is simplified, right? So En itself is equals to d E t over d theta, as you can see here. So recap, previously we have our velocity vector v equals to v in the tangential directions et, right? So if you want to determine the acceleration vectors, then we have our a, we do differentiations, then we have a equals to dv dt, right? So equals to dv dt et plus v det dt. So you can see that the accelerations now decompose into two components. One is in the directions of et, another one is v det dt. And with the relationship of En vectors that we have built just now, then we can later on determine these components in terms of En vectors. So the velocity vectors, v is equals to v in the directions of et vectors. Then the accelerations, like what we have derived just now, is equals to dv dt in the direction of et and v de dt. And we can rewrite it in terms of dv dt in the direction of et plus v de d theta ds dt. And earlier we have determined the relationship of En vector with the t d theta. Then we also know that from our elementary calculus, 1 over rho, the radius, is equals to delta theta over delta s. The curvatures of our circles with the radius that give us the relationships. So rho, or the radius, d theta is equals to ds, or d theta ds is equals to 1 over rho, right? And we also know that ds dt equals to v, the velocities, magnitudes. So if we substitute all these known data to the acceleration vectors, then we have our a acceleration vectors here is equals to dv dt et in the direction of et plus v square over rho En. So here we have our v, we have our En, d theta ds is 1 over rho, this one we have a v, so basically it's giving us v square over rho in the directions of En, right? So we have decomposed the acceleration components into et directions and En directions, the tangentials and also the normal directions. Where in the tangentials direction, we call it a tangentials components of accelerations. Basically, it reflects the change of speed. dv dt is a change of speed, whereas the normal components reflects the change of the directions, v squared over rho. The tangential component may be positive or negative. The normal components always point towards the center of path curvatures, right? So this is always point to the centers of the curvature. The tangential, it could be positive or negative, depends on our velocities. So in the case of particles velocity increase, so AT is positive, and the vector components of AT is in the direction of the motions. And if the speed of the particle decrease, AT is negative, then AT point against the directions of the motions. All right. So if you can see that this is our AN, this is our AT, then our resultants, our A itself, probably it will lay on around here is our A. And we can see that these vectors does not lay along the tangents of the curvatures of these particles. Looking at these accelerations equations in tangentials and normal components, the accelerations of a particle will be zero only if both its components are zero, both this dv dt or v squared over rho equal to 0. So for a particle moving with constant speed along the curve, the accelerations will not be zero. We have the normal components here is a non-zero. dv dt is equal to 0. So the accelerations will not be 0 in this particular case. So in summaries, these tangentials and normal components are most often used when the particles of interest travels along a circular path, or when the radius of curvature of the path is to be determined. Please take note that the unit vectors ET is tangent to the path of the particles and is aligned with the velocities, while the unit vectors En is directed along the normal to the path and always point toward its center of curvatures. Normals and point towards the center of curvatures. Please also take note that when the particles move along this curve, the directions of these two unit vectors are constantly changing. So if your particles now is at around here, right? So your unit vectors ET now is tangents to the curve will be at here, ET. Then when you have your unit vector En will be going towards the centers, then that will be your En. So the directions of the two units vectors are constantly changing when they are at different position at the path curvatures. In certain problems of plane motions, the positions of the particles is defined by its polar coordinates, radius r, and theta, the angles. Here, basically, we are decomposing our positions of the particles in terms of radius and transverse components. When the radius r and the theta angles are known functions of time t, so meanings when the radius change with times or the angle change with times, the positions of the particles or the velocities and the accelerations of these particles can be represented in these polar coordinates or decomposed in terms of radial and transverse components. So these are some of the examples. For instance, by knowing the distance to the aircraft and the angles of the radars, air traffic controller can track the aircraft. Another example is the fire truck ladders can rotate as well as extends. The r changing, rotates is the theta changings. Then the motions of the end of the ladder can be analyzed using these radial and transverse components. So here we can see that the positions of the particle P is expressed as a distance r from the origins O to P. These define the radial directions ER in these directions. The transverse direction is perpendicular to the ER directions. We call it E theta. That basically relates to the angles theta. So if we have the positions of a particle P in terms of the R equals to R in the directions of ER, then we differentiate once to get the particles velocity vectors can be represented by this. V equals to R dot ER and R theta dot E theta. And if we differentiate again the particles velocity vectors, then we will have the accelerations vectors. So it can be expressed as A equals to R double dot minus R theta dot square in terms of ER directions. Then we have R theta double dot plus 2R dot theta dot in the directions of E theta. So let's have a look how these velocities and accelerations vectors is being derived. Given the position of this particle P is R in the directions of ER. And recap back what we have learned just now in the tangentials and normal components, where we build the relationships between the En and DETs. So we'll just draw it here. So we have recap backs. We have this in terms of ET primes. Then we have this delta ET. Then we have this delta theta. And we are saying that En is equals to dEt over d theta, right? So when it is the delta theta is approaching 0, then it is normal or perpendicular to our ET, and that is our En. So making use of these relationships, then we can build the relationship between E theta with the ER d theta and ER with the relationship of dE theta d theta. So how we can do is looking into this is the ER. Then if we put here is our ER primes, that is our delta theta, right? So here will be our delta ER, right? So when it is this delta theta is approaching 0, then our this unit vector is perpendicular to our ER, which is here is our E theta. So E theta is equals to d ER over d theta. That gives us this. Similarly, if we have looking into this E theta vectors, we have another one at E theta primes. So this is delta theta. So here is our delta E theta. So when this delta theta approaching 0, then we will have a unit vector that is perpendicular to our E theta, which is similar to ER but in the negative directions. So it's negative ER. Okay, it's going in. So we have our E negative ER equals to D E theta over D theta. So making use of these two relationships, we can determine the derivative of the ER dt by applying the differentiation rules, the ER d theta dt, and we know that the ER d theta just now is E theta and d theta dt. We also can find the derivative of the E theta dt is equals to dE theta d theta dt, and we also know that this dE theta d theta is our negative ER, so it equals to negative ER d theta dt. Recap back, giving the R equals to RER, the positions vectors, then the velocity vector will be the derivative of our positions vectors. So our V equals to the differentiations of this R dt. You can further expand to dr dt in the directions of ER and R der dt. And just now we have obtained the ER dt is equals to d theta dt E theta. So we can write our velocity vectors as dr dt ER in the direction of ER plus R d theta dt in the direction of E theta. So here R dr dt is our R naught. Then we have this R d theta dt is our theta dot. So in the directions of radial ER, we have R dot. In the directions of transverse or theta, we have R theta dot. Similarly, we can also further differentiate it another times to get our particles accelerations vectors. So we know that the accelerations is dv dt. So we differentiates with respect to time these velocity vectors, this. All right, then we will have here, this is our R dots, this is our R theta dots. So by doing the differentiations rules, we will have our accelerations vectors equals to, as you can see here, d2r dt square ER. Then we also plus dr dt, okay, dr dt, but differentiates der dt. Then we plus this particular part dr dt, d theta dt, E theta. Then we have R d2 theta dt square E theta, and finally R d theta dt, and this dE theta dt. So all these can be further substitutes where we have d2R dt square is our R double dots, right? Then we have our dr dt is our R dots. Der dt is what we have here, theta dot E theta from here. Then we have our dr dt is R dot, d theta dt is theta dot. Then we have d2 theta dt square is theta double dot. Then we have our d theta dt is theta dot. dE theta dt is what we have from here, is equals to theta dot ER, but is negative. So group them in terms of the radius components ER and the transverse components E theta. Then we have our acceleration vectors in terms of radius CR. Components will be R double dot minus R theta dot square. In terms of our transverse directions, we will have this R theta double dot plus 2R dot theta dot. As I mentioned earlier, these radial and transverse components is particularly convenient to be used to solve problems when our R, the radius, or our theta, the angles, are the functions of t. Basically, the R and the theta change over times. In the case of the R is constants, so when we have a R is constant, so meaning to that probably it will go into one circles where your R is constants, and in the directions of here is our ER, and here will be our E theta. Right. So if R is constants, then our R dot is equal to 0, R double dot is equal to 0. Recap what we have learned in radius components of ER. We have our velocity in these directions, VR equals to R dots, whereas our acceleration in this direction, AR, is equals to R double dot minus R theta dot square. And in the transverse directions, E theta, we have our V theta equals to R theta dot, and our A theta equals to R theta double dot plus 2 R theta R dot theta dot. So looking at this, R is a constant value, and the derivative first and second will be all 0. Then our AR can be simplified in terms of only negative R theta dot square, whereas our A theta can be simplified to R theta double dots. The R dots here will become 0. Here the R double dot will become 0. So we know that our theta dots here is our angular velocities omega. Our theta double dot is our alpha, or usually is what we call angular accelerations. And in terms of velocity, V is actually equals to R omega, and our A tangentials is actually equals to R alpha. Alright, So our omega here is equals to V over R. Our alpha here is equals to theta double dot equals to A D over R. So these radial accelerations and transverse accelerations then can be further uh, simplified to negative R V over R square, and it will be equivalent to negative V square over R. So this will be in what we call radius directions or radius components accelerations. And you can actually see that it is similar to what we have derived previously in tangential and normal components. In this case, it is similar to what we have the normal accelerations equals to V square over R or rho in the normal directions. The only difference is the negative sign. On the other hand, for our transverse directions accelerations, we have our R theta double dot is our A tangential accelerations over R. So it's actually equals to our tangential accelerations in this transverse directions. Or here we can say that it is in our tangential directions. So in other words, under a constant radius, we can either express our velocity and accelerations in terms of radial and transverse components, or it's more convenient also to derive or express it in terms of tangentials and normal components, because here our radius is not functions of time, it doesn't change, it is constant over times. Then it will be more convenient or easier to express our positions or velocities and accelerations in terms of our tangentials and normal directions. So here we have our En, here we have our Et. So compare side by side, we know that our Et and E theta unit vectors Et is similar to what we have seen here, E theta, whereas our Er, the radius component, is opposite directions with our normal components. So that is why here we have a negative in the radial directions, the normal directions, we do not have the negative sign. So this is all about kinematics of particles, particularly under curvilinear motions. So we have learned how to decompose the positions in terms of vectors, velocities vectors, and also acceleration vectors. So we can decompose it in terms of rectangular components. Then particularly useful when we are dealing with projectiles motions. We can also decompose in tangentials and normal components. So this velocity and acceleration can be expressed in these components, and is particularly useful when we are dealing with the known curvature path or the radius. In the case of when the radius and the angles are changing over times, then we can represent our velocities and accelerations in terms of radius and transverse components. It will be more convenient to use this component to solve this type of problems.